Hey everybody, this is Mr. Woodward. In this video, I'm going to talk about how it's really important to identify and understand initial and final moments in linear motion problems. And so in this case, we're going to be looking at an object that's rising and falling under the influence of gravity alone. So let's just take a look at this description as I begin. The big three kinematic equations use the terms initial and final to limit the analysis of an event between a starting and a stopping moment, right? The starting moment is the initial, the stopping is the final. It's kind of like editing a film clip. You get to decide when you want to start and when you want to stop so that only the main event is showing. Choosing the initial and final moments is one of the most strategic ways to solve motion problems, but it's often the most confusing for students. So let's take a look at an example to understand how the initial and final moments can change depending on your analysis. And so here's the example down here, okay? Suppose a boy threw a ball up in the air, and we're talking about this picture on the right. Suppose a boy threw a ball up in the air while standing on the edge of a cliff. The ball's position each second would look like the picture to the right, okay? So we're outlining the position of the ball. As it's rising, the change in position shortens. As it falls, the change in position lengthens because it's accelerating under the influence of gravity. So, and then here's our given. At t equals 0 seconds, assume that v sub y, meaning the vertical velocity, is positive 29.4 meters per second. Complete the table below to show how the ball's change in vertical position, delta y, depends on the initial and final moments that you choose, right? So there is a sense in which you can affect the delta y depending on how you set up the initial and final moments. Okay, so I've broken up the motion into these sort of three sections. We have the ball is rising, then the ball is falling, and then looking at the entire trip rising and falling, okay? So let's start with this first part where we've got the ball rising. And actually, before I do that, I want to use this. The initial vertical velocity is 29.4 meters per second. So I'm going to start to annotate this picture. And by the way, there is a hidden given in this problem, which is that if you know anything about objects that are rising and falling under the influence of gravity, I should say rising or falling under the influence of gravity, then the acceleration, if it's an idealized situation, if there's no air resistance, then the acceleration in the vertical direction is going to be negative 9.8 meters per second squared, okay? So we're going to go ahead and assume that. And here at 0 seconds, as soon as the ball is released from the boy's hand, we can say that the velocity here, right, is positive 29.4, and that's meters per second, okay? Then 1 second later, the ball is rising, but as it rises, it's slowing down a little bit because it's going against gravity. So what happens to the velocity? Well, it drops. And how much does it drop by? 9.8. So the velocity here at 1 second is going to be 19.6 meters per second, right? That's just 29.4 minus 9.8. And then at 2 seconds, the velocity is now, and I should have put a positive here. Now at 2 seconds, the velocity is positive 9.8 meters per second. And then at 3 seconds, which is when it's at the peak, the velocity is 0. That's because 9.8 minus 9.8 is 0. Then the ball begins to fall, and as it falls, it continues to accelerate, but it's gaining speed in the negative direction. So now at 4 seconds, which is just 1 second after the peak, the velocity is now negative 9.8 meters per second, right? I'm just continuing to subtract 9.8 every time. At 5 seconds, the velocity is negative 19.6 meters per second. At 6 seconds, the velocity is negative 29.4 meters per second. And then at 7 seconds, it's going to be subtracting 9.8 again, which means the final velocity just before it hits the ground is going to be negative 39.2 meters per second, okay? Again, this is assuming this initial velocity, and it's assuming that the ball is in perfect free fall, meaning that there's no air resistance, and it's accelerating at exactly negative 9.8 meters per second squared. Okay, so now that we've outlined the velocities each moment in time, let's take a look at this data table. So when the ball is rising, we've got an initial time and a final time. So while the ball is rising, the initial time is going to be the 0 seconds in the picture, right? That's this moment. When the ball, the final time while the ball is rising is going to be here at the top, right? That's the end of the rising motion. So that's going to be 3 seconds, right? That's considered the final, T-final during the rising motion, okay? During the rising motion, the initial vertical velocity is positive 29.4 meters per second. And during the rising motion, the final velocity is the peak, which is 0 meters per second, okay? And we're going to do this delta y in a moment. We'll come back to that. All right, now let's look at when the ball is falling from the peak height to the bottom of the cliff, okay? So only looking at the falling motion, starting here at the top, ending here at the bottom. Now we have a new initial and final moment, okay? So now the initial time is 3 seconds, right? Because we're starting at the peak height. Then the final time would be 7 seconds. In this falling motion time interval, the initial vertical velocity would be 0 meters per second, right? That corresponds with the 3-second moment. And then the final vertical velocity would be negative 39.2 meters per second. Okay, that corresponds with the 7-second moment. All right, we'll come back to this part at the end. All right, then let's take a look at the third option here, which is the entire trip from the boy's hand to the peak to the bottom of the cliff, the whole motion, okay? Now, the initial time is 0 seconds, and the final time is 7 seconds. We're looking at the whole trip. The initial vertical velocity is as soon as the ball is released from the boy's hand, positive 29.4. The final vertical velocity is just before the ball hits the ground, which is negative 39.2 meters per second, okay? So we can choose the initial and the final moment depending on our analysis. All right.